There are 8 of them. In addition, QCD has a property called color, which plays a similar role to that of electric charge in QED. So basically, if you take QCD and QED together, there are certain properties that are kind of transpiring, as you can see, as we are mentioning them. These are basically mass, charge, and color. Depending on which particle you are, or basically, if I told you the mass of something, the color of something, and the charge of something, you would basically then give me the answer, okay, you're talking about this particle. I'll show you the table of particles really soon here, but basically, depending on your mass, charge, or color, you would tell me that it's an electron, or you would tell me, oh, it's this neutrino that you're mentioning, or you would tell me it's this quark. So depending on those, and actually that another property too that I should mention is spin. So depending on mass, charge, color, or spin, these are all quantum properties, quantum states, if you will. All of these particles that we have just now mentioned, I know quite a few of them, and we will summarize them all in a nice table very soon. I'll show the picture of the table. But all of these particles, all of them, they sound like there's a lot of them, right? And this is one of the complaints of classical physicists, which is that particle physics just has so many of these particles. And, you know, it seems like this jungle of particles, and people want to know sort of what is the broader picture, the bigger picture that can explain all of these particles. That is a complaint of classical physicists. For example, when people were trying to come up with, for example, a grand unification theory, something that they would like to address is this particle jungle. There's just so many particles and so many states and properties and whatnot, and we just don't want to deal with it in this way. And can we have a bigger picture way of dealing with this, a theory of everything, right? But keep in mind that everything that we understand or have measured or know about these particles that we just mentioned so far in this live, those have to all fall out of this new theory. If there is a grand unification theory, everything that is known already by particle physics has to kind of be outputted by that theory. You can't just have a theory which then does not give you the fermions or the bosons, or it just leaves out something maybe like color or quarks or something, right? Everything has to be explained by this grand unification theory, which actually makes it quite challenging. Because as you can see, as much as the particle jungle can be inconvenient for people who don't want to deal with a lot of different variety, but at the same time, it's also known things. And if you don't have a grand unification theory outputting the known things, then you cannot accept that grand unification theory as the reality. Okay, so that's what's really going on here with the grand unification theory and its challenges. Partly the challenge is, there are other challenges too, but partly the big challenge is that it really has to explain all of these quantum properties as well that have been found and delivered by quantum mechanics and particle physics. So namely, once again, the mass, the charge, the color, and the spin of these different particles that we've just now mentioned have to all come out of a grand unification theory. Better do if you're going to explain and call something a theory of everything, okay? So I'll tell you a little bit about the electroweak theory because he talks about it next, and then we'll leave it there. The drive for unification is the next topic he discusses because it's the natural next topic. And this thing that I just said is literally what's kind of going on here. Like once you have all these particles, and I'll show you in the table, right? We've discussed leptons, we've discussed leptons, we've discussed quarks, we've discussed bosons, and the different flavors of each one. So electron, neutrinos, quarks, bosons, all of these are the different particles, and there's different types of them in each of these families. And they all have a mass, a charge, a spin, and a color. A grand unified theory, once again, has to explain these, and things better be falling out of the theory naturally to encompass all of these, okay? Is it possible, taking a cue from Maxwell's influential unification of electricity and magnetism in the 19th century, so in the 1800s, to put all QED, the weak interactions, and QCD together in a single overarching theory.